Students, in this class we are going to see about wave motions. What is wave and what are the types of wave and what are the characteristic properties of the wave and what is longitudinal and transverse wave and how we are going to calculate the velocity of the transverse wave. We are going to see this wave motion in detail. You all know what is wave. Wave is nothing but a disturbance which is produced with the medium. What is wave? That's a disturbance which is produced in the medium due to the vibration of the particle involves its mean position. That is, there is no movement of the particles. The particles are vibrated in its mean position. Just to and fro motion about its mean position. So due to the vibration of the particles, a disturbance is produced in the medium. That is called as wave. What is wave motion? This wave which is generated in the medium is propagated through the medium only due to the vibration of the particles about its mean position. Let us see the definitions here. Wave motion is the transfer of energy and momentum from one point of the medium to another point of the medium without actual transport of matter between 2 points. There is no movement of the particles, only the vibration of the particles. Okay. Next one is classification of wave motion. So here the waves are classified into two types. One is mechanical waves, another one is non-mechanical wave. This non-mechanical wave is electromagnetic wave. That is the example for this non-mechanical wave is electromagnetic waves. These mechanical waves are it definitely need a medium. This non-mechanical waves does not require any medium. So these mechanical waves are classified into two types. One is based on the vibration of the particles in the medium. Next one is based on the energy transfers. So based on the vibration of the particles, the mechanical waves are classified into two types. One is transverse wave, another one is longitudinal wave. And based on this energy transfer, mechanical waves are classified into two types. One is standing wave, another one is progressive wave. In this class, we are going to deal with this transverse waves, another one is longitudinal waves. In the forthcoming class, we are going to see about the what is standing waves and what is progressive wave in detail, and we are going to see about the what are the wave equations for the standing waves and the progressive wave. Okay, let us see about what is transverse wave. So this transverse wave, the particles are vibrated perpendicular to the direction of the wave. But in longitudinal waves, the particles are vibrated parallel to the direction of the wave. In this particle vibration, the waves are classified into two types. One is transverse wave, another one is longitudinal wave. In the transverse wave, the particles are vibrated perpendicularly. In longitudinal waves, the particles are vibrated parallel to the propagation of the waves. Okay, I think you are clear. So this is the waveform of the transverse wave. Okay. So see, so this upper region is called as crest. What is crest? That is the region of maximum upward displacement is called crest, and region of maximum downward displacement is called as trough. This downward maximum is trough, upward maximum is called as crest. So in this, the particles are vibrated perpendicular to the direction of the wave. Example for this transverse wave is string waves. For example, we have imagine I am holding a string or you are holding a string. One end of the string is fixed and another end is we are holding. Imagine we are holding the another end of the um, um, another end of the string on hands. Okay, what happens when you are giving a jerk to the another end of the string? So the strings are moved in this form, and that is also similar to the transverse wave form. Okay. So in this transverse wave, the particles are vibrated perpendicularly And this in this transverse waveform, you know what is crest and what is trough. Crest is upward displacement region is called as crest, and downward displacement is called as trough. Next one is longitudinal wave. So this in this longitudinal wave, the particles of the medium vibrated about the equilibrium position in a direction parallel to the direction of the wave. The particles are vibrated parallel to the direction of wave is called as longitudinal waves. Example for this longitudinal waves is called sound waves in a tube. The sound waves which are filled in the tube. What can so imagine this is the see this is the longitudinal waveform or imagine a string. What happens when we are stretching a string? It is extended. When we compress the string, when we push or when we are applying a force to the string, it is compressed. This region is called the compressed region, and this region is called the rarefaction region. And in transverse waveform, we introduce two parts. One is crest, another one is trough. In longitudinal waves, we denoted two regions. One is compression, another one is rarefaction. The difference between the transverse and longitudinal. The main difference between the transverse wave and longitudinal wave is here that in transverse the particles are vibrated perpendicularly. In longitudinal wave the particles are vibrated parallelly. Next one is characteristics of wave motion. Characteristics of wave motion. Let us see the characteristics in point wise. First point, so the disturbance in wave motion, the disturbance travels through the medium due to the repeated periodic oscillation of the particles of the medium about the main questions. You know, the wave is transformed, the wave is propagated in the medium due to the vibration of the particles. Next one is the energy and momentum are transferred from one point to another without the actual transfer of the particles of the medium. There is no movement of the particles. The energy is transferred from one particle to another particle. Definitely, there will be a phase difference between the two particles because the one particle start vibration after that it transfer the energy to the another particle because there is a phase difference between the first particle and the second particle or first particle and the fifth particle likewise. Okay, there is a phase difference between the particles of the medium. Next one is there is no correlation between the velocity of the particles of the medium and the velocity of the wave generator. So the both are different. That is the velocity of the particle vibrator is different from the velocity of the wave it is propagated in the medium. Next one is for a given medium, the velocity of wave motions remains constant, while the particle velocity changes continuously during its vibration. That is, the velocity of the wave it is constant through the medium. One is initially a wave is generated and is propagated with the particle velocity means through the throughout the medium it maintains the constant velocity. So the particle waves is generated due to the vibration of the particle. The vibration is maximum at one position and zero at the another position because the displacement is at the displacement because just to and fro motion no. So it is maximum at one end and zero at the another end. Up to now we see about what is wave and what are the types of wave and what are the characteristics of the wave. Now we are going to see about velocity of how can we calculate the velocity of a transverse wave. Okay. For this, let us consider or let us imagine a transverse wave. Okay, you are taking a part of a wave. You are not considering a full waveform. You are considering a part of a waveform. So imagine, you see here, I am considering a particular part of the wave, and on this part I am denoting 2 points. One is A, another one is B. Okay, with this I am note up here. I'll draw a circle clearly. So in this point, compare these two parts, both are similar. And this point is taken as A, and this point is taken as B. And small dl represents the distance between 2 points A and B. Okay. Imagine that this is the wave, transverse wave, or consider this is the string. Okay, whatever it may be, it's okay. From C, draw one line and it end at O. At O, draw two lines which will meet at A and B. The angle formed between A and C is equal to del theta, and the angle formed between C and B is equal to del theta. Okay. That is I'll give you an overview. How can we calculate the velocity of the transverse wave? Imagine a string. Okay, when the transverse wave is produced due to the movement of the string. So when we are applying a movement to the string, what happened? A force is acting on the string to generate the transverse wave. That force is called as tension force. Okay, first force. Next force is when at this point towards the center, a force is acting. That force is called as centripetal force. Okay, two forces are acting. One is centripetal force, another one is tension force. At equilibrium condition, these two forces are equal. By equating these two forces, we are going to calculate the velocity of the transverse wave. Okay, so we are considering a transverse wave. We are considering a part of the transverse wave. So I'm taking this part up here, and from this, considering a origin, I'm drawing one circle over this. It is having the radius capital R. That is radius of the circle is R. Imagine a circle over this point that is having the radius capital R. I didn't mention here capital R here, but you note down this. That is the radius of the circle is capital R. Okay, and the two forces are acting on the string. One is tension force, another one is centripetal force. This tension force is resolved into two components. One is capital T denote the tension force, and this central part O denote the centripetal force. Okay. This tension force is resolved into two components. One is horizontal component, another one is vertical component. At this end also, it is resolved into two components. One is horizontal, another one is vertical. This horizontal component is taken as T cos del theta, and the vertical component is taken as T sin del theta. Here also it is taken as T cos del theta, and here it is taken as vertical components on this left side is taken as T sin del theta. These horizontal components are equal and opposite to each other, so we cancel together, and we are considering only the vertical component. Okay. Okay. So imagine I am explaining the figure here. For us to determine PQ with the string. Imagine your PQ is the string, that is two ends of the string. No, one is PQ, which is the end of the string. One end is taken as P, another one is taken as Q. Okay, T, the capital T is taken as tension along the x-axis, tension force along the x-axis, and a small portion of the string is equal to AB, and it is taken as DL. That is circle having the radius capital R. Towards O, a centripetal force is acting. That centripetal force is equal to mv square divided by R. Here small m is the mass per unit length of the string. So instead of m, you are taking as m dl v square divided by R. V is the velocity of the string. M is the mass per unit length of the string. This tension force can be resolved into two components. One is horizontal component, another one is vertical component. I already told you, one is horizontal, another one is vertical. Horizontal is T cos del theta, and vertical is taken as T sin del theta. These horizontal components are cancelled each other. We are considering only the vertical components. There are two vertical components, no? So we are summation of two gives two vertical component is given taken as 2t sine del theta is equal to 2t del theta. Del theta is very small. Sine of del theta is very also, it will also use a very small value. So we are neglecting the sign of sine del theta. We are considering the only del theta. Okay. From the figure, you consider 2 del theta is equal to AB divided by R. We know AB is equal to DL divided by capital R equal to, instead of 2 del theta, we are substituting this DL divided by R. So finally we can write the previous equation as T dl divided by R. You know, I'm repeating here. So we are horizontal components are cancelled each other. We are considering only the vertical component. The sum of two vertical component 2t sine delta equal to 2t del theta. We are neglecting the sign here. 2 instead of 2 del theta, in the diagram, imagine 2 del theta, take the 2 del theta equal to AB divided by R. We know AB is equal to BL. So from this equation, instead of 2 del theta, substitute the 2 del theta is equal to DL divided by R. Okay. This is the, here we see about the what is the expression for the centripetal force. This is the expression for the tension force. Okay, now we are going to at equilibrium condition. These two forces are equal. Which two forces? Centripetal force, another tension force. Now I am equating these two forces. Centripetal force MTL V square divided by R equal to tension force TDL divided by R. By equating these two forces, what need? We need only the velocity of the string. So V square is equal to T divided by M. R we can write as V is equal to square root of T divided by M. So what is the velocity of the transverse wave is equal to square root of what? Square root of T divided by M. Okay. I just recap the velocity of a transverse wave. We are considering a string. We are considering a part of the string, and we are drawing one. We imagine one circle over the string, and we imagine we are considering the two forces which are acting on the string. One is centripetal force, and the one is tension force. And at equilibrium, we are equating these two forces, centripetal force and tension force. From this equation, we will arrive at velocity of the transverse wave E square is equal to T divided by M. Next one is frequency of a vibrating string. Okay, consider two ends A and B. This A and B region is taken as, this is the nodal region, and the region between A and B is the antinodal region. We know the velocity of a transverse wave is given by V is equal to root of T divided by M. From the figure, L is the length between the 2 points. The smallest is the length between the 2 points N and N, or between 2 points A and B. Imagine a string is plugged in the middle. That is, we are vibrating the string means a transverse wave is produced. This the velocity of the transverse wave is equal to V is equal to root of T divided by M. This region, that is the end of at two ends of the string, is got taken as nodal node. At the middle of the string is taken as anti-node. We are one cycle, that is lambda is equal to what? Here we are considering a L is equal to lambda divided by half of the waveform. If a full waveform, if a completed waveform is taken as wavelength lambda, we are considering only the half. So lambda divided by 2 is equal to L. If n is the frequency of the vibrating string and lambda is the wavelength of the wave, velocity is equal to frequency into wavelength. So then comparing these two equations, which two equation? Velocity of the transverse wave with the velocity of the what? This comparing the equation 1 and 2, that is n lambda is equal to root of t divided by this standard equation for velocity, and this is the velocity of this transport wave. By equating these two equations, from this we can arrive at final equation for the frequency n is equal to 1 divided by lambda root of t divided by m. Okay. From the figure we can say L is equal to lambda divided by 2. So instead of lambda, we can substitute lambda is equal to 2L, n is equal to 1 divided by 2L root of T divided by M. This is the fundamental frequency of a vibrating string or frequency of the transverse wave. Initially, we see the velocity of the transverse wave. After that, we calculating the frequency of the transverse wave. Velocity of the transverse wave equal to V is equal to root of T divided by, and the frequency of the transverse wave is equal to n is equal to 1 divided by 2L root of T divided by M. Let us see what is harmonics and overtones. Okay. So, the integral multiple of the frequency is termed as harmonics. So what is the integral multiple of the frequency? The frequency which is above the fundamental frequency is called as harmonics. That is the frequency 2 and 3 and 4 and 5 and 6 and 7 and 8 and 9, and that is the multiple of the fundamental frequency is termed as harmonics, and the overtone means that is the frequency which is above the fundamental frequency is called as overtones. It may be an first harmonic, or it may be a fifth harmonic, or it may be an eighth harmonic. That is called as overtones. Okay. From the figure, consider the frequency as we are. I am taking here the frequency as capital N. Don't confuse with the denomination. So frequency, fundamental frequency is taken as N. Second, the frequency is taken as 2 1. Third frequency is taken as 3 and 4 and 5 and 6. Here the frequency is 144 Hz at the double, 288, 422, 576 likewise. Okay. Let's see that is what is harmonics. I already explained you, but here to see the definition here. The harmonic, the integral multiple of the fundamental frequency is called as harmonics. It may be on second harmonic, 2 and is the second harmonic, 3 and is the third harmonic. Okay. 5 and is the fifth harmonic, and so on. So, okay. Now we are explaining the that is I denoted in the figure that waveform is a standing waveform, or it is called a stationary waveform. Why? What is stationary waveform? That is the transmit, that is incident wave and the reflected wave superimposed on each other and form a stationary wave pattern is called as stationary wave. Let us imagine two identical waves travel in opposite direction. Let these waves meet each other. That is, the travel in opposite direction means that incident wave is travel in one direction and the reflected wave is travel in opposite direction. These two waves meet each other. The resulting wave is obtained by superimposing one on to the other. It is called the standing wave or stationary wave. On the stationary wave, we denote 2 points. One is node, another one is antinode. Okay. which is nodal region, that is the at frequency two ends which are do not the point which are fixed together, that the point where it is meet together is called a nodal region, and the maximum amplitude region is called as antinodal region. Okay, but the transverse wave we will do 2.1 is crest and is trough. In longitudinal wave we will do 2.2 regions, one is compression and another one is rarefaction. In stationary waves we are denoting two regions, one is nodal region, another one is antinodal region. Okay, now you can able to, now I suppose you are all clear about this harmonic. The harmonics, I am explaining the harmonics and overtones in the stationary waveform. What is stationary waveform? Superimposition of two waveforms. What are the two waveforms? One is transient waveform, another one is reflector waveform. These two waveforms are superimposed on each other, and yes, the standard wave pattern is formed, that is called as stationary waveform. In this stationary waveform, there are two regions. One is nodal region, another one is antinodal region. Okay, after that, what is harmonics and overtones? Harmonic is the integral multiple of the fundamental frequency is harmonic. Okay, the first harmonic is the fundamental frequency. Second harmonic is the 2n, that is second frequency 2n, and third harmonic is 3n, and so on. Next one is overtone. An overtone is defined as any frequency produced by an instrument which is greater than the fundamental frequency. Any frequency which is greater than the fundamental frequency is called an overtone. It may be a 5n or it may be a 6n. Okay, likewise. Okay. But harmonics is defined as the integral multiple of the fundamental frequency. In overtone, it is the frequency above fundamental frequency. Okay. It may be initially it may be a second harmonic. Initially it may be a third harmonic or sixth harmonic. So on. Okay. There is no constraint in this. The frequency, any frequency which is greater than the fundamental frequency is called as overtone. So overtone is an integral multiple of fundamental frequency or called as harmonic. That is any multiple of frequency, any integral multiple of frequency is called as overtone. The instrument produce only the harmonics and no overtones. All the instruments, if the wave generated is harmonic now, all the instrument will produce an harmonic waves. Okay. I suppose you are all are clear about the harmonics and overtones. Okay. This last suppose you're all clear about what is waves, what are the types of waves, and how can we calculate the velocity and frequency of the wave, transverse wave, and what are harmonics and overtones. So in this class we see what are the there is a waveform, there is transverse wave and longitudinal wave. In the forthcoming class, we will see about the what is progressive and stationary waves, and how can we calculate what is the wave equation for the progressive wave and stationary waves. Okay, thank you.